Just start recording. Yes. Okay.
Okay, so I'll share my screen. Sharing is not turned on.
It's not turned on. Wait. Try now.
Yes. Okay. Can you see the screen?
Yes.
Yeah.
Awesome. Okay, so uh, I'll talk about introduction to Fourier, short time Fourier, and wavelet transform. So I just put together this presentation, and we'll see how it goes. So this is a basic introduction to these frequency domain analysis techniques, and we'll try to understand why we use them and how they work. Just the basics. Okay. So first of all, why do we even need frequency domain analysis? So when we look at a time domain signal, for example, let's talk about audio signals. Audio signals are time series signals. There is a lot happening in audio signals. There are frequencies from 20 hertz to 20 kilohertz, and you cannot see those frequencies when you're looking at a time domain signal, which is just a waveform. Now, let's say you are working on an application of audio source separation. So, for example, you have a speech signal and there is a disturbance in the middle of that signal. For example, someone shut a door. Now, you want to extract that noise from the speech signal. Now, looking at the time domain signal, you'll not be able to tell where that noise occurred because time domain signal looks very complicated. It's a sinusoidal signal. But when you transform to frequency domain signal, you'll be able to see where those extra frequencies are there in the signal. So it becomes easier to extract and filter those frequencies. So there comes the need for frequency domain analysis. Now, the first thing in frequency domain analysis is the Fourier transform. So Fourier transform breaks down a signal into constituent sinusoids of different frequencies. So the figure on the left hand side is a time domain signal. So we have time on the x-axis and the amplitude of the signal on the y-axis. So whether it is an audio signal, EEG signal, or any biomedical time series signal, or any time series signal, for the matter of fact, it looks like this. Now Fourier transform converts this signal to the one which is on the right hand side. So on the x-axis, we have frequency, and on the y-axis, we have amplitude. So it transforms the view of the signal from time-based to frequency-based. This is another good example of frequency transform, Fourier transform. So this blue signal is a time domain signal, which is made up of these two sinusoids. So this is the first one with lower frequency and higher amplitude. And this is another one with slightly higher frequency and lower amplitude. And when we add these two signals up, we get this signal. Now, when we take Fourier transform, it transforms this view to this view. So it tells us that there are two frequencies in the signal, and this frequency has this much amplitude, and this frequency has this much amplitude. And it all happens using this scary looking formula. So it's minus infinity to infinity f t to the power minus j omega dt. So let's try to understand how this formula works and how it magically converts this time domain representation to this frequency domain representation. Okay, so let's start with the Euler's formula, which is e to the power j omega t equals cos omega t plus j sin omega t. I think everyone knows this. Here, t is the time and omega represents the frequency of the signal. Now let's also consider an imaginary plane. So the x-axis is the real axis and the y-axis is the imaginary axis. And if we connect this plane to this formula, then the cosine term is basically representing the real axis and the sine term is representing the imaginary axis because there is a j here. So omega is representing the frequency and t is representing the time. So when omega t is 0, then we know that cos 0 is 1 and sine 0 is 0. So as we saw, cos is the real axis. So cos 0 is 1, so we come to 1 and sine 0 is 0. So on the y-axis, we are at 0. So we are at point A. Okay. Now, when omega t is pi by 2 or 90 degree, cos pi by 2 is 0 and sine pi by 2 is 1. So we go to 0 on the x-axis and we go to 1 on the y-axis. So we are at point B now. So what's basically happening is omega here is constant, which is representing the frequency of the signal, and t is the time which is changing. So what's happening is that e to the power j omega t goes around 0 in this circle as the time changes with the magnitude of 1. Is this clear? Or should I repeat it?
No, it's clear.
Okay, awesome. Now let's consider a sinusoidal signal. So this is a pure cosine wave, and the frequency of this cosine wave is 3 hertz. So it's completing 3 cycles. So 1, 2, and 3. 3 cycles in 1 second. So it has a frequency of 3 hertz. Now let's multiply this signal with e to the power j omega t. Now the maximum amplitude of this signal is 1 and the minimum is almost 0. So when we multiply this signal with e to the power j omega t, we get something like this. So e to the power j omega t has a magnitude of 1, which is constant. Now when xt at time equals 0, xt is 1. So we are at 1 here. And at this time point, it's almost 0. So we are somewhere around here. Then it again goes to 1. So we come back to 1. Then it again goes back to almost 0. So we also go back to almost 0. Now there are two frequencies here. The first is the frequency of this signal xt, which is 3 beats per second or 3 hertz. The second frequency is the frequency of this omega term, e to the power j omega t. So that is the frequency with which we are wrapping xt around the circle. So right now this is half rotation per second. So what's happening is that we are going from 0 to pi from here to here in 1 second. So in 1 second, this signal is completing 3 cycles. And we can see that if we look here, this is 1 cycle, this is the second cycle, this is the third cycle. Okay. So we go from 1 to -1 in 1 second, and here we complete 3 cycles. So the first frequency is of xt, the second frequency is of e to the power j omega t. E to
Um,
the power,
can
yeah.
you tell me why we have multiplied xt with e j omega t? What was why have we multiplied xt and j
Oh,
with
yeah.
e? Uh,
We, in just a second, we are getting there.
okay.
So e to the power j omega t is also given as e to the power. So omega is basically 2 pi f, where f is the frequency, actual frequency. So if f is 1, we are we have 1 rotation per second. So we will complete one full circle in 1 second. And if it's 10, then we'll complete 10 circles in a second. Now, what happens when this winding frequency matches the frequency of this signal? So when this frequency matches the signal, then for a single rotation, a single cycle of this signal, we will complete one full circle, right? The frequencies are the same. So this is completing 3 cycles in a second. And when this frequency is also the same, we will complete 3 circles in a second. So for a single circle, we have one cycle. Now our graph looks like this. So we start from 1, we go to almost 0, following the cosine wave, and then we go back to 1. So this is one cycle of the cosine wave and one full circle completed around 0 with magnitude of 1. So this is xt to the power j omega t. Now Fourier transform is basically an integral over this from -infinity to infinity. What that basically means is that we add up all these values. So if we add all these values, we'll get a point somewhere here in the middle. Okay. Now the interesting part is that if the winding frequency does not match the frequency of the signal, this center point will be somewhere very close to 0. But when it does match with the signal frequency, it will be away from 0.
Can you explain that again? I didn't catch that.
The last part?
Yeah. So how does it, is that, are those two figures the same, like the cardioid plot and
Ye-
the other plot?
Yeah.
Yeah. So,
So in this figure, the rotation frequency is half cycle per second.
okay.
And the signal frequency is 3 cycles per second.
Yeah.
Okay. So when we go from 1 to -1, that is 1 second. And then again -1 to 1, that is 1 second. So we get this graph. So 3 cycles in a second. Okay. Now, if you sum up all the values of this graph, the resulting sum will be somewhere very close to 0.
Okay.
Okay. But if this winding frequency is equal to the frequency of this sinusoidal signal, then you will get something like this. So you are completing one cycle of the cosine wave, which is this from here to here. So
Mhm.
1 to almost 0, then back to 1. Okay. So 1 to almost 0, then back to 1. So
So
when
when the
you,
winding frequency matches the signal frequency, right?
yes,
Oh, okay.
yes, winding frequency matches the signal frequency, and then you take the integral of all these values, you'll get a point which is away from 0. It will not be close to 0.
Okay.
This basically represents the frequency content of your signal. So if you have multiple frequencies in the time domain signal, then for each of those frequencies, when you take the integral of this plot, you will get a value which is greater than 0. And if you plot those, you'll get something like this. So for all other frequencies, you have
Wait,
something
I have
around
a
0.
question.
Yeah, yeah, yeah.
So we multiplied xt with e to the power j omega t, but in
Right.
the formula it's e to the power minus j omega t, right?
So that minus basically decides the rotation. So
Oh,
e
okay,
to the power
okay,
j
okay,
omega t goes counterclockwise, e to the power minus j omega t goes clockwise.
okay. That's all.
But yeah,
Hmm.
it's the same. Yeah. So ultimately, you get a graph like this. So this is basically this integral value on the x-axis, the amplitude. So for all the frequencies which are not there in the signal, you get a value close to 0. And for the frequencies which are there in the signal, you get a value which is higher than 0. So this is how you get your Fourier transform. Is it clear?
Yeah.
Yeah. So
Yeah.
this scary looking formula is actually pretty simple. Okay. So let's look at some papers, some recent papers, ML related papers which are using Fourier transform. So an example is this FED former, which is frequency enhanced decomposed transformer. This is an ICML paper, if I'm not wrong, with more than 3,000 citations. Yeah, ICML. So these are just examples. I mean, I've not uh, read them in detail, but they have this frequency enhanced block. So what they're probably doing is they're taking Fourier transform of the signal, then they are filtering that signal when they are doing inverse Fourier transforms or something like that. We also have this Freak LLM. This is frequency aware large language model for time series forecasting. They're also using Fourier transform. So in all these implementations, they use an algorithm called fast Fourier transform, which is a very computationally inexpensive way of calculating Fourier transform. Then this is for time series forecasting. This is a NeurIPS 23 paper. So they are using MLPs in frequency domain. So they are first taking the Fourier transform of the signal and they're applying MLPs there. Then we have neural operator, which also uses Fourier transform. So Fourier transform, filtering, Fourier inverse, then activation. This is the neural operator. So this was the Fourier transform. Now, what's wrong with Fourier? So when we take Fourier transform, we lose the time information. So if we look at this plot, we have time and amplitude, and after Fourier transform, we have frequency and amplitude. There is no time. So Fourier transform cannot locate drift or trends or abrupt changes and beginning and ends of events. So if a particular frequency was there in the signal for a short duration of time, Fourier transform will not be able to locate the location of that frequency. Wow. Okay. So we have two types of signals, stationary and non-stationary. So in stationary signals, the frequency content in the signal is constant. So in this example, this waveform is made up of three sinusoidal waveforms, 2 hertz, 10 hertz, and 20 hertz. And the amplitude of these three signals is constant throughout the signal. So if we take the Fourier transform, we get something like this, three peaks around 2, 10, and 20 hertz. In non-stationary signals, the frequency content changes over time. So from time 0 to 0.4, we have 20 hertz in this signal. 0.4 to 0.2, there is 10 hertz. Then 0.7 to 1 second, we have 2 hertz. So the frequency content is changing But when we look at the Fourier transform, we again see three main peaks, one at 2, one at 10, and one at 20. Now, by looking at these frequency domain representations, we cannot tell what the time domain signal is and what frequency content is where in the time domain signal. This is the biggest limitation of Fourier transform. Another example of chirp signal. So in the first signal, frequency goes from 2 hertz to 20 hertz. In the second signal, frequency goes from 20 hertz to 2 hertz. But if you look at their Fourier transforms, they're identical. So Fourier transform gives what frequency components exist in the signal. Time and frequency information cannot be seen at the same time, and time frequency representation of the signal is needed to overcome this limitation. So a very logical solution to this is short-time Fourier transform or short-time Fourier analysis, which is also called Gabor transform. In short-time Fourier transform, what we do is we divide our time domain signal in smaller windows or segments. And then we take the Fourier transform of each segment separately. So for each segment, we have frequency by amplitude, which is Fourier transform. And then we have multiple segments along the time axis. So if we concatenate them, we get a graph like this. So on the x-axis, there is time. On the y-axis, we have frequency. And each of these time bins are basically Fourier transform of a single window. So pretty intuitive. Now, STFT also has some limitations, which is basically time frequency trade-off. So the time frequency localization depends on the window size, which is the width of this window. For wide window, we get good frequency localization and poor time localization. Now, another thing I forgot to mention about Fourier transform is that, so yeah, so this is the Fourier transform. Now, the number of frequency bins in this graph. So if this is the minimum frequency and this is the maximum frequency, then the resolution of this x-axis or how many points we have on this axis depends on the number of samples we have in the time domain signal. So if there are 10 samples in this time domain signal, then we will have 10 frequency bins in the Fourier transform, in the frequency representation of Fourier transform.
Where does this come from? Like, why is it dependent? Is there some reason behind it?
This, I think, comes from this formula only, because you are multiplying your signal with e to the power j omega t, so you get, and this multiplication is element wise. So you get the same number of frequency bins as there are in the time domain signals, right?
Okay.
Yeah. So if our window size is large, then we'll have more samples in the time domain signal of which we are taking the Fourier transform. And more samples in the time domain signal means more time points, more frequency bins in the Fourier transform. So we get a good frequency resolution. But at the same time, because we have increased the window size, the number of windows in the signal will decrease. So if our window is almost this size, we can fit how many? 1, 2, 3, 4, maybe 5 windows. But if I double the window size, we'll be able to fit hardly 2 or 3 windows. So our time resolution will decrease. But if I make this window narrower, then our time resolution will increase. We'll be able to fit maybe 6 or 10 windows in the signal. But the number of time points in a single window will also decrease, and hence the resolution in the frequency domain. So there is this time frequency resolution trade-off in short time Fourier transform. So good frequency localization results in poor time localization. Good time localization results in poor frequency localization. So a compromise between time-based and frequency-based views of a signal. Both time and frequency are represented in limited precision, and the precision is determined by the size of the window. Once you choose a particular size of the window, it will be same for all the frequencies. So in real world, the signals require a more flexible approach, especially varying the window size. So let's take an example of, let's say, audio signals. So in audio signals, we need good frequency resolution for lower frequencies. For example, let's say you are tuning a guitar and you have a string at 440 hertz, which should be at 440 hertz, but let's say it's at 435 hertz, and you'll immediately notice the difference when you're playing the guitar that, okay, this 440 hertz thing is out of tune. But if you are talking about, let's say, 8 kilohertz frequency or 10 kilohertz, if you go from 10 kilohertz to 10.5 kilohertz, you will not be able to notice the difference just by listening to it. So in real world signals, we use good frequency resolution for low frequencies, and it doesn't have to be as good for higher frequencies. But because higher frequencies change very fast, we need good time resolution for higher frequencies. And even though it would be good to have good time resolution for lower frequencies as well, but even if we don't have that, it's okay, because lower frequencies basically represent drift in the signal. For example, if there is a 0.5 hertz frequency in the signal basically moves very slowly up and down. So even if we don't have a very good time resolution for lower frequencies, that's okay. So that's where wavelet comes. So first of all, what is a wavelet? Wavelet is a waveform of effectively limited duration that has an average value of 0. So an example is given here. This is the normal sine wave, which is of infinite duration. This is a wavelet, which is of limited duration. And if you add all these points, you'll get 0. These are some examples of other wavelets. Again, all of these are of limited duration with an average value of 0. So let's look at the continuous wavelet transform. So as we saw, the Fourier transform is integral from minus infinity to infinity. Then multiplication of the signal ft with e to the power minus j omega t dt. Similarly, CWT is defined as sum over all time of the signal multiplied by scaled and shifted versions of the wavelet function, which is given as psi. So it's again integral minus infinity to infinity, ft, which is our signal, and then psi t dt. So psi here is the wavelet, which is one of these. And there is this concept of scaling and position shifting that we'll see in a minute. And the result of the CWT are many wavelet coefficients, which are a function of scale and position. So let's look at what the scale and position is. So scaling means stretching or compressing the signal. So this is ft, which is psi of t. A is basically a scaling factor, which is 1. So it goes from 0 to almost 2000. Now, if we do shy of 2t, so we have the scaling coefficient is now half, and the time duration of this wavelet becomes half. So instead of going from 0 to 2000, it's now going from 0 to 1000. And if it's 1/4, it becomes shy of 40, and the duration is 1/4 of 2000. So this is what scaling means. And shifting is basically shifting the wavelet on the x-axis throughout the signal. So this is shy t, this is shy t minus k. So we have shifted it by k samples. This is the wavelet function. So shy of x is given as 1 upon root a, which is a normalization term. Shy of x minus b divided by a, where b is the shifting coefficient and a is the scaling coefficient. So let's see how CWT works. So it's basically the sum over all time of the signal multiplied by scaled and shifted versions of the wavelet. So what you do is, first of all, you take a wavelet and compare it to a section at the start of the original signal. And by comparison, it means you multiply the two signals and you add all the values of this multiplication.
So is it like a convolution happening over the signal?
Yeah, kind of,
Okay.
yes. So you calculate the number C, which is basically the multiplication and summation of all the time points of the wavelet and the signal. So C represents how closely correlated the wavelet is with this section of the signal. So it's basically a correlation. The higher the C is, the more the similarity is. Okay. Now you shift the wavelet to the right and repeat the above two steps until you have covered the whole signal. So again, so from here we come to this part of the signal. We calculate this number C by multiplying these two signals and adding up all the values. Then again, we'll shift the signal to the next part of the signal, the wavelet, and we'll again compute the C for that part. Once we have covered the whole signal, we will scale the wavelet and then repeat steps 1, 2, 3. So when we scale the wavelet, the frequency or content of this wavelet changes. So here we have a slightly higher frequency wavelet, and when we stretch the wavelet, the frequency is slightly lower. Now we'll do the same operation for this scale and for every scale. So it looks kind of like this. This is your wavelet, and you are shifting and multiplying the wavelet with the signal. So what do we get after this? So this is your time domain signal. So you have time and amplitude. This is your frequency domain signal. You have amplitude with frequency. This is your short time Fourier transform. So you have time and frequency with these bins. And with wavelet, you get something like this. So this is scale versus time. So as scale is how we stretch the wavelet. Now, the only difference between these two is that this is representing lower frequencies near zero and higher frequencies as we go up on the y-axis. This is the opposite. So this is wider wavelet, so it's representing lower frequencies. And as we come to zero, it represents higher frequencies. There is a way to invert this, but this particular graph is showing it this way. So as we can see, for lower frequencies, the scale resolution or the scale is basically representing frequency. The frequency resolution is better as compared to higher frequencies. But time resolution is worse for lower frequencies as compared to higher frequencies. So we get good time resolution in higher frequencies, and we get good frequency resolution in lower frequencies. Now, why does this happen? So for lower frequencies, we are basically stretching this wavelet so that the frequency of this wavelet is low. Now, when we stretch this wavelet, let's say our signal is this long, and our wavelet is this long. Now, after this portion of the signal, we'll move on to the next portion of the signal. So we only get two coefficient values because after two, the signal is finished, right? Now, if I scale this wavelet and the length of this wavelet is half of what it is right now, we'll be able to fit four wavelets in the signal. So we'll get four coefficients. And that is exactly what's happening here. So we have first two coefficients for the lowest scale, then we have four coefficients, then we have eight coefficients. So that's why our time resolution changes. This is an example of CWT. So this is a hyperbolic chirp signal. And when you take CWT, it looks something like this. So there is a way to convert this kilogram, which is this scale versus time, to a frequency versus time representation. This is the frequency versus time representation. So as we can see, this moves like this. So for lower frequencies, we have fewer number of time bins, and as the frequency increases, our number of time bins increase. And we can also see that this frequency axis is logarithmic. So from 0 to 10, we have really good frequency resolution. We can see individual frequencies. So this is 1, 2, 3, 4, 5 hertz. So this is very good frequency resolution. But if we come here, this is 100 and it will be around 1000 here. So this resolution is much lower as compared to this resolution. So this was the continuous wavelet transform. Now we come to the discrete wavelet transform. So calculating wavelet coefficients at every possible scale is fair amount of work, and it is computationally expensive. And it also generates an awful lot of data. So what if we choose only a subset of scales and positions at which to make our calculations? It turns out rather remarkably that if we choose scales and positions based on power of 2, which is also called dyadic scales, then our analysis will be much more efficient and just as accurate. We obtain so that is basically the discrete wavelet transform. So in DWT, what we do is we divide the signal into approximations and details. We have a signal, we divide it into two parts. One is approximation, which is A. The other one is details, which is T. Now, approximation is basically an approximation of the original signal. You just apply a low pass filter. So you remove the high frequency content. You have the lower frequency content, which is an approximation of the signal. Details part contains all the higher frequency content. Now, the cutoff frequency of these two filters is basically sampling frequency by 4. So if your sampling frequency is Fs, your time domain signal can contain frequencies up to Fs by 2. This is the Nyquist theorem. And you basically divide that frequency range from 0 to Fs by 2 in half. Dyadic scale, powers of 2. So this is 2 to the power. This is half basically. So this goes from 0 to Fs. This is Fs by, 0 to Fs by 2. This is Fs by 4. So you have two components. Now, the problem is that if we perform this operation on a real signal, we wind up with twice as much data as we started with. So for instance, if the original signal consists of 1000 samples, then the approximation and detail each will have 1000 samples. So to correct this, what we do is we introduce the notion of downsampling. This simply means throwing away every second data point. So we downsample it, and the result is we get half the number of data points. So now it looks something like this. So 1,000 samples, we apply high pass filter for details, low pass filter for approximations, and then we downsample both. So we get 500 coefficients. Now this is an example. So this is a sinusoidal signal with some noise introduced to it. So if we apply a high pass filter, it will remove all the low frequency content, which is basically this sinusoidal frequency, and it will retain all this high frequency noise, which is this noise here. And the approximation part will contain all the lower frequency content. So we can see that it has less higher frequency noise, and it's an approximation to that signal. Now, what we can do is we can repeat this process, and we get this multiple level decomposition. So the decomposition process can be iterated with successive approximations being decomposed in turn, so that one signal is broken down into many lower resolution components. So we have this detail and approximation. After that, we take this approximation signal and we repeat this process. So we divide this approximation into two parts, higher frequency and lower frequency. After that, so this is the first approximation. Then we get a second approximation and second detail signal. And then we can repeat this process however times we like, however many times. Okay. So this is basically your discrete wavelet transform. Now, every detail and approximation has different frequency component. So even though we did not make like a spectrogram or a scaleogram, we have multiple signals with a which contain a band of frequencies, a limited band. So CD1 will contain the upper half of the frequencies of the whole signal, and CA1 will contain the lower half of the frequencies. Now, from that lower half of the frequencies, CA2 contain will contain the half of those lower half frequencies, the lower half, and CD2 will contain the upper half. So this is the basic idea behind discrete wavelet transform. This is again an example. So this is first detail and first approximation. Then we get the second detail and second approximation, and so on. This is another approximation. So this is a sinusoidal wavelet type of signal. And these are all the approximations of the signal. So the first approximation is a higher resolution and very close to the signal. And as we keep doing the same thing, the resolution decreases, and so does the frequency component of the signal. So this was a general introduction to these
So,
three transforms. Yeah.
so is this like you are doing this process and then you are calculating wavelet transform on the different
No, no,
signals?
no, 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 no. So this is also known as multi-resolution analysis. So what you basically want to do is you want a time frequency domain representation, right?
Mm-hmm.
Now we kind of have that here. We have decomposed our original signal into multiple signals. Each signal has time component, and each signal has a limited amount of frequencies.
Okay.
Okay, so first detail has the highest, most frequencies of the signal. The second detail has the frequencies below the first detail. The third detail has the frequencies below the first and second detail. And ultimately, the last approximation has the lowest frequency. So all these signals have different frequency components of the original signal. So basically, you have decomposed the original signal into multiple signals with different frequency components. And because each of those signals is again a time series, you still have all the time information. So it's kind of a time frequency analysis, slightly different from the continuous Wavelet transform. But this becomes very computationally inexpensive as compared to the continuous Wavelet transform.
Mhm.
So this was pretty much it. We can look at some more papers. So these are some papers that have used short time Fourier transform. So this is phase and harmonics aware speech enhancement. So short time Fourier transform is very widely used in audio applications and speech related applications. Uh, this is fast and universal speech enhancement with studio like quality. It's a New Lips 24 paper. Good, very good paper. Uh, how do you remove this? Then this is, I think, a wavelet paper. So wavelet, continuous wavelet transform is mostly used with time series and ML related applications as a feature extraction step. So if you want to look at the frequency content of the signal, you take, let's say, an audio signal, take the wavelet transform, and you give that to a model. So the model can see the whole frequency content along the time axis. So that is where wavelet is mostly used. Discrete wavelet transform is a bit more interesting. So it's being used in other ways as well. So this is a very interesting paper. This is attention wavelet neural operator. So they have kind of embedded the discrete wavelet transform inside the layers of a neural network. So in each step, what you do is in each layer you decompose the signal into discrete and then you do some operations, attention and all, and then you take the inverse wavelet transform to get back the signal. And they're able to do this because a discrete wavelet transform is much more computationally efficient as compared to continuous wavelet transform. This is audio source separation using discrete wavelet transform. So these are kind of the applications where these things are used. So that was pretty much it. Thank
It,
you. Let
it,
me know if there are any questions.
Thank you for a great presentation. But I have a question. Like, do you
Yeah.
have a comparison on people using frequency domain for learning and what happens if you are just using time series as it is instead
So
of
there,
that? Like,
so I was not able to go through these papers, but I think there is a good comparison in this paper. Frequency domain MLPs are more effective learners in time series forecasting. This is a good NeurIPS 23 paper. And again, I didn't get a chance to go through the paper, but if I'm not wrong, so they have compared their method, the frequency domain method, with these time domain methods. So this patch TST is a very famous transformer based method, which is completely time domain based. So autoformer is again time domain informer. These are all time domain based methods. So their results are pretty good, outperforming the time domain methods.
Mhm.
Yeah.
Is it possible for you to send the links or like the papers for us?
Yeah, absolutely. I'll share
Awesome.
these on the group.
So I think a better thing would be if you can just attach all the links in your presentation and
Okay, okay.
share your presentation as it is because it's a really good presentation.
Yeah, it
Okay.
is. It's a really good
I'll,
one.
I'll, I'll do that. Thank you.